Hello and welcome to another video. In this video we're going to be working on find the city with the smallest number of neighbors at a threshold distance. And in this one there's n cities from 0 to n minus 1, and you have an array of edges where edges are from to weight, kind of like yesterday. And you have bidirectional weighted edges between from and to given an integer distance threshold. Return the city with the smallest number of cities that are reachable through some path whose distance is at most distance threshold. If there's multiple such cities, return the one with the greatest number. And that the distance of the path connecting I and j is equal to the sum of the edges weights along that path. So in this first example, here's the graph, and here's what's reachable within the threshold. So from 0, you can go to 1 with a distance of 3, or 2 with a distance of 4, and you can't reach anything else. From 1, you can go to these 3, from 2, you can go to these 3, and so on. So you want to return the city with the biggest number with the smallest amount of cities reachable, which is going to be this case, because 0 and 3 are tied, so you want to return 3. And then example 2, kind of similar. So city 0 has the least, so that's the one you want to return because the threshold is 2, so this is what you can reach from 0, and that's it. So basically, I'm going to assume you know Jigsawer's algorithm for this one, because it's basically just like doing this a bunch of times. But assuming you know Jigsawer's, if you don't, there's literally problems that are like implement Jigsawer's algorithm on LeetCode. You can just look that up and start with that. The constraints are pretty small. And so to do Jigsawer's, the constraints are small enough basically where like you can do Jigsawer's starting from every node. So because you can do Jigsawer's from every node, basically what we can do is we can say like, okay, let's just start at a node and let's see everything we can reach from that node with the shortest path that the threshold is whatever it is. So in this case from 0, we have like this node and so on. And basically you're going to get like a visited set starting at every single node. And so it's basically just Jigsawer's, except when you're figuring out like, do I want to go to the next edge? You want to make sure that the total distance is under this or equal to it. Kind of like yesterday, very similar. So we can do Jigsawer's from every node, then we'll have a visited set. So after we visit starting from like 0, let's say we'll have a visited set of like we visited 0 and 1, and then from 1 we visited 1, and what else can you visit with distance of 2? 4 and 0, and so on and so on and so on. So for every single one of these you'll get a visited set. So basically the number of nodes you were able to visit is the length of the visited set, and you don't want to count the node itself. So the length of the visited set minus 1 is going to be how many nodes you were able to visit. And then you just, what we're trying to do is we're trying to minimize that. So we can go node by node, just return how many nodes we were able to visit, and then give us the one that we were able to visit the least from. And to make sure that we follow this, the biggest number if there's a tie, when we compare, so we'll have some like result nodes we visited. If our current is less than or equal to result, then we update our result that way. And we're going to be visiting the nodes 0 to I. So if there's a tie, we're going to visit the one with the bigger number last, and that will override it. So it's basically that. We're just going to start with every single node, do the normal heap Jigsawer stuff, and just the only constraint is we have to make sure we're under this distance threshold, which is like 2 lines of code difference. Yeah. And I will say in Java, the runtime isn't going to be great here because you're going to be, or at least the way I'm going to be doing it, I'm going to be using like a queue or a heap, a set, all this other stuff. So I think if you use Floyd-Warshall instead, you actually get much better runtime because you can just use like a 3D array or something. But I personally haven't learned Floyd-Warshall, and the Floyd-Warshall runtime is usually n cubed, and the Jigsawer's is n cubed if you start at every node. So I think Jigsawer's starting at every node is like n squared log n, or from one node is like n squared log n. So from every node it's n cubed log n, which is basically the same as Floyd-Warshall. And I think learning an algorithm for basically no purpose whatsoever and roughly the same runtime is kind of like eh. So you could learn Floyd-Warshall and you could code this up doing an array, and specifically in Java you'll get much better runtime. But if you use like heap and all these other like heap, hash map, all these things in Java are slower. So my solution in Python got like pretty good runtime, but in Java it's going to be significantly slower. So just whatever your preference is. And I'm not trying to make like solutions that are specific to Java runtime optimization or anything. Okay. So yeah. So first we're going to make a graph, and like I said, you can make a map here. You can also make an array, which will be like and basically anything you use an array for instead of a graph or instead of a map or a set or something will give you better runtime. but I'll just make a map because that's how you're going to do it in most languages. So I'll just make a generic solution. So we'll say map, and basically we're going to have a map from every node to every other node, and we want to record the weight. So it's going to be like map integer, and then this will be like an int array, I think. Because for every node, we're going to have the node that it goes to and the distance. Call this graph. Okay. And we'll also have like a initial result array. So we'll say int array result. And so we're going to have the node, and we'll just make it default -1. And we'll have the like number of nodes we could visit. We'll make that infinity so we can minimize later. I don't know why I can say float int. Can't do that on the 6. Do max. Okay. Yeah. So then we're gonna go through all our edges. So int array edge and edges, and we're gonna get the 3 things. So the x value, the y value, and the distance. So 0. Okay. And then, so the best way to do it I found in Java is if you want to have a if you want to have a map of like lists or something, and you want to create a list when it's not there, you can use compute if absent. So basically you do this. So compute if absent, you give it some key, and if it doesn't exist, you give it a function. So we can just do a basic function that we don't need to use input variable for, and we just say we want to make a new list here. So essentially what this will do is like if x doesn't exist in the graph, it will make that list for you. And then to that, if it does exist, we'll get it. We want to add a new edge or a new like child node. And it's going to be the child node and the distance. And the same exact thing for y. So same exact thing. Okay. And then what we want to do, this is kind of slow, so like I'm not sure if it's, I guess we'll see if it gets fixed. Anyway, so then we already have our result, and now we just basically want to loop through values 0 to n and make a heap for all those. So let's go back, fix that later if I need to. Here, okay. So we're gonna loop from 0 to n. Yeah, this is what I was saying. It's kind of weird. Like it says it's not working, but then it is working. So anyway, and for each one of these, we basically just run Drixters on it. So we're gonna say make a visited set, and then we also need to make a priority queue. And it's going to be of the format of int array, and we're going to make a new one. And I think because you have an int array, not just like an integer, you have to give it a comparison function. So we're just going to say AB, and we want to just compare the, so it's going to be format distance and then the node. So we just want to compare on the first value, and we want a min priority queue because we want the minimum distance. So it'll be like this. And then we want to add our current node to that heap. So, oh, I forgot to give it a name. So we want to just say like heap add int array, and it will be the node and the distance. Actually, it'll be distance then node. So distance will be 0, and the node is the current node we're starting at, which is I. And we want to say while we have a heap. So while it's not empty, pop the node. So and then get the values. So distance is going to be the first one, and the node will be the second one. And if it's already in visited, we can just continue. You can write this in like a bunch of different ways. You can also, instead of a visited set, I think you can use a visited map. And then you can make sure not to put nodes into the heap that have a longer distance, something like that. It's not going to matter too much though. Yeah, so we want to say here, like if visited contains our node, we want to continue because we've already seen it. Otherwise, we want to add it to visited, and we want to go through all of its children. So I think we still have to check if it's in the graph, because I think you can have a graph that's not fully connected. I don't think they said it was fully connected, so contains, oops. So if it contains the node, then we want to check the children. Get node. And then we want to get the child node and then the distance, so we can say child node equals child 0. So our format that we stored in the graph is node and then distance, the other way from the heap. So child distance. And basically for this node, we want to check have we visited it yet, and also if we add this child distance, so like for our node to get to the child and our distance to get to the node, all that together needs to be under the threshold. So we can check for that. So if visited contains child, if we already visited the child, we don't need to go there because we're using Trickstras. So yeah, we already been there in a faster way. And if distance plus child distance together need to be under the threshold. Otherwise it's too far and we don't want to add it. So if this is the case, we can add it. I do think, yeah, you can improve performance a little bit by, I mean, you can improve performance a lot more by using floated warshell in Java, but if it's not Java specific, you can also improve performance by, instead of using a visited set, use a visited map, and then you can calculate, like, for a child, calculate the distance it took to get there, and then if we're putting in a bigger number, then don't use that either, because you don't want to put a number into the heap that's bigger than one in there. But it's not really going to matter, so I'm not going to do that. So basically we're going to add the distance plus child distance and the child node. Yeah. And then what we want to do is we want to check the length of our visited set. So if so result 1 is how many, like, what's the best cities or nodes we visited. If that's greater or equal to visited size -1, that means this result is better than the one before or tied, so we want to store this one. So we could say result equals new int array. And then we can make this the current node and visited size -1. Okay. And then we want to return here result 0 is the node, and see if something's broken still. Okay, looks like it is. Let's see. Incompatible types, bad return type. Okay. So this is map integer int array. This should not be an int array, actually. This should be a list of int arrays. Okay. Cannot find symbol. Priority queue int array heap. I think this one should be fine, unless I'm missing something stupid. Let's see. Oh, right, I need a minus. Okay. Alright, getting the wrong answer, so let's just double check. So x is this is fine. X at y, this is fine. Visited heap a0 minus b0, it's fine. Distance then node, so we want to make sure we're putting things the right way. We are. Visited add if it contains. Child node child distance is correct. That's correct. Okay, so our error is just we need to calculate this after we do this whole heap thing, so it's just in the wrong place. So pretty simple. Needs to be here. Okay. And yeah, so like I said, the runtime is going to be worse than these, because if you look at these for Java, they're basically all using arrays. So that's the only difference. But in another language, it's fine. So like if you look at basically the same exact thing in Python, it's good. So they're just language dependent. Okay, so let's figure out the actual complexity. Yeah, so Dijkstra's is basically like, oh, so what are we doing? We're taking every single edge and we're putting that in the graph. So let's call that E, I guess. And then, yeah, then we're taking every single node and we're doing something for that. So this like V. And then for every single node, we're doing Dijkstra's. So worst case, every node is connected to like every other node or something. Yeah, so I think for every single node, you can have like, I think this is like n squared total. And then you're doing like heap pushes and heap pops. So I think it's like something like e squared log. And then, so you're storing nodes or edges. I guess you're storing like edges. So it's something like this, something along these lines. Basically, it ends up being roughly v cubed or n cubed or whatever if e is like v squared, something like that. Okay. Yeah, and then space. So we're storing every single edge, and we're also storing nodes that we're visiting, I guess. So that's like already e plus b. And then in the priority queue, I think you can store something like you can probably optimize it, but I think in the priority queue at one time you can store something like e squared. So maybe it's like this. I never get this right. Okay, I think like also people write the complexity and like the worst case. I think they're like off a lot. But yeah, I think it would be something like this where you can probably have like every edge in the priority queue at a time. Or I guess if you optimize it, you would have less. Yeah, so I think you can actually optimize this to be v plus e for Dijkstra's. But in my current one, I don't think that's the case. And like I said, the way you would optimize it is instead of a visited set, you would have a visited map. And then you would just check like if I have this edge already in my priority queue and it's a smaller distance, then I don't need to have it. Actually, no, that would still be e squared. Because you can put in your edges, like you can put in your edges and you can put in the same one over and over and over if the distance keeps being smaller, which is possible. It'll be some weird case, but yeah, I think it's something like this. Even if you're optimizing, like you can still run into the case where, yeah, you're putting it in and you keep putting in a smaller distance. Yeah, so basically this is just Dijkstra's with, like I said, this little addition here from every node. You could do Floyd-Warshall as well. I would probably recommend just sticking with Dijkstra's. I think I know Bellman-Ford. I've almost never used Floyd-Warshall. It's basically never needed in any algorithm because Dijkstra's will pass for everything that Floyd-Warshall will, and Dijkstra's is just more generic. So if you want to learn it, you can. I didn't bother. And yeah, it's going to be all for this one. So hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.